Okay, 3, 2, 1, it's jam.
What's up, science fam? Living things and the things that living things produce have so much variety. Like, if you've ever noticed body odor of different people, different scent each time. How is this possible? Does it maybe have something to do with chemistry? Of course it does. So our topic for this session are organic compounds. So this is how carbon and hydrogen create diverse types of molecules. So for this session, we're going to explain how properties of carbon result in different compounds, describe different types of organic compounds, and explain how functional groups modify the properties of organic compounds. Let's do this. So what makes a compound organic? It's not about being free range or pesticide free. No. When we're talking about compounds, your organic compounds are compounds that have a lot of carbon hydrogen bonds. So if your carbon bonds with hydrogen and there's a lot of it, it's most likely an organic compound, and they tend to be very complex and diverse, like in this diagram here. Your inorganic compounds, on the other hand, are kind of dull if you compare it with organic compounds. Now, some of the properties of organic compounds, in particular, let's focus on the flammability and the solubility in water. For the flammability, organic compounds tend to be flammable. This is indicating how much energy there is in your organic compounds. Your organic compounds tend to be very complex and large, and because of the carbon-hydrogen bonds, there's lots of energy inside them, which can be released by burning. Your inorganic compounds, on the other hand, have less energy, or it's not as accessible as inorganic compounds. You can't just burn them. Solubility, on the other hand, since organic compounds are made of covalent compounds and are very complex, they tend to be insoluble in water, meaning you can't dissolve them in water, at least not very easily. Your inorganic compounds, on the other hand, tend to be soluble because inorganic compounds tend to be ionic. They tend to have positive and negative charges, which water can dissolve very easily. So what makes carbon and hydrogen so special? Why are organic compounds their own special category? So that's because carbon is perfect as a backbone for complex molecules. Why is that? Because carbon is the smallest atom that can form the maximum number of covalent bonds, 4 covalent bonds. If we look at the number of valence electrons here, carbon has 4 valence electrons. So oxygen, on the other hand, only has 2. Nitrogen has 3. Hydrogen has 1. Any other atom that can form 4 covalent bonds is much bigger than the carbon atom itself. So it's the best possible atom for complex molecules, while hydrogen makes the perfect filler for complex molecules. So since it's so small, it rarely gets in the way of other atoms if it wants to incorporate other atoms, right? So again, carbon and hydrogen are perfect for making very big, complex molecules. So there's many kinds of organic compounds, but we're going to focus on the ones that are highlighted. So organic compounds can be classified into aliphatic and aromatic, and the aliphatic can be further classified into these things. So we're going to focus on these broad categories to introduce you to organic chemistry. So hydrocarbons are a class of organic compounds that are made only of hydrogen and carbon. So let's start with those hydrocarbons. So we have aliphatic and aromatic. Aliphatic just means that they have regular carbon-hydrogen bonds, whereas aromatic ones have benzene rings, which means that these have resonance. They have alternating single and double bonds. We'll explain that in a bit. All you need to know is that aliphatic is vanilla or normal bonds, and aromatic has special bonds that are more stable. So let's get aliphatic compounds out of the way first. Let's discuss those first. Your aliphatic hydrocarbons can be divided into 2 categories. We have saturated and unsaturated aliphatic hydrocarbons. Your saturated hydrocarbons are saturated because they are filled with hydrogen. They're filled with the filler atom. So since they're filled with the filler atom, they have as many single bonds as possible. So they only have single bonds. Your unsaturated hydrocarbons, instead of having as many hydrogens as it can take, it forms double bonds between its carbons. So it can be double bonds or triple bonds, resulting in an alkene or an alkyne. So again, if there's only single bonds, it's an alkane. If there's at least one double bond, it becomes an alkene. And if there's at least one triple bond, it becomes an alkyne. And the priority here is that if there's even one triple bond, it becomes an alkyne. Even if it has a ton of double bonds inside that atom, the moment there's a triple bond there, it's an alkyne. Your alkene is next in the hierarchy, and then alkane is the last. Alkane being the one with only single bonds, absolutely no triple or double bonds. In terms of reactivity as well, your alkynes are the ones that tend to react with other compounds or atoms the most compared to alkenes and alkanes. So these are some examples of an alkane, your ethane. Your ethene is an alkene and your ethyne is an alkyne. Take note that the name says what kind of hydrocarbon it is. Informs you as well if there's a double bond or a triple bond in the organic compound. So this this entire slide just summarizes the past slide in table format. Very good for notes. I'm going to get my face out of the way. You can pause it on this part so that you can take better notes. You're welcome. Let's continue. Alkenes, the double bond ones, can actually transform. For every double bond, it can have two different forms. This is due to isomerism. So alkenes can have cis or trans isomers. What does this mean? Cis is a Latin term that means same side. So it means that both ends of the organic compound on opposite sides of the double bond are on the same side. So this is a cis isomer here. This sample diagram here, you can see the CH3s are on the same side compared to the double bond. On the other hand, in a trans isomer, trans means across. So the ends are on opposite sides. So this is the double bond. One of them is here, and on the other side, it's across the street. So let's think of the double bond as a street. If it's on the same side of the street, it's cis. If it's on opposite sides or across the street, it's trans isomers. So isomers in general have the same chemical formula but different structures. And having different structures actually makes them have different properties. So just, twisting your alkene can make it a completely different organic compound. How do people even name these things? Well, there's rules for naming them, and we're going to discuss these different rules. So these are the steps of naming an organic compound, and we're going to do this one by one. We're going to try this one by one. First, we identify a parent chain, then identify substituents, then we number the carbons of the parent chain, use prefixes to indicate the number of similar substituents, and use number labels of the parent chain to show where all the substituents are. What does that mean? This is easier with pictures. So let's try this. Let's try this compound. So we don't have the name, but we're going to name it based on the rules. So first rule, identify the parent chain. So the parent chain, again, is the longest chain of carbon. So if we try to start counting here, with this carbon, we'll get 1, 2, 3, 4, 5. But if we start counting here, we get 1, 2, 3, 4, 5, 6. Let's try starting from here again. 1, 2, 3, 4. 4, 5. The maximum number, the longest chain of carbons, is the 6 carbons over here. So that 6 carbons, according to the naming system, we have to have a root name. So in our root name, the number of carbon atoms in your parent chain corresponds to a particular root name prefix. So 1 is meth, 2 is eth, and so on. For 6, it's hex. So let's note that down. 6 carbons in their parent chain. We start with hex. So the root name is like the family name of your organic compound, all right? So it's color-coded in this example. So the family name is very important because it communicates the length of the parent chain and if it's an alkane, alkene, or alkyne. So let's move on. The second step is to identify the substituents, or if there's any double bonds or triple bonds, or if there's any branches in your hydrocarbon. So in this case, we have one branch. So this weird offshoot here is referred to as a branch, and we have one double bond here. So let's note that down. One branch, so that this branch is just one carbon long. So it's a one carbon long chain. And for branches, the naming convention is to take the prefix. So in this case, there's only one carbon in the offshoot or the branch. So we take meth and then we add YL. So methyl. So methyl is the name of that branch. And for your double bond, that double bond is assigned that it's an alkene. So we have the suffix "ene" from alkene. So that will go to your root name. So again, that "ene" is a suffix, the hex from earlier is the prefix, so our root name is hexene, hexene. So we'll note that down before we take the next step. So again, we noted down that the root name is hexene, and we have a substituent of one methyl and one double bond between carbons. So in step number 3, we have to number the parent chain, and we have to start at the end with the nearest substituent. No matter where we start, if we start at this end or this end, the substituent is always the same. It's like 1, 2, 3. Then we have the first substituent. If we start at this side, it's 1, 2, 3. We get the first substituent. It doesn't matter in this case. But in other organic compounds, it might just be very important to pick which side you start from. Again, start at the end that's nearest to a substituent. So now that we have the numbers for our parent chain carbons, we have to go to step number 4, use prefixes to indicate the number of similar substituents. So this is the prefix system that we're talking about now. So it's a different prefix system if we're just trying to show how many there are. So in this case, there's only one of each substituent. So if there's only one, there's no need to put mono, because it's understood that there's only one if you don't put any of the other prefixes. So that one methyl and that one double bond, we don't have to put any special prefix, right? So we move on to the next step. Use the number labels of the parent chain to indicate position of the substituents. That just means that these numbers that we put on the parent chain, that's used to indicate position. We're like, where are the different substituents or special stuff? So the methyl branch is connected to carbon number 3 over here. And the double bond starts at carbon number 3, connected to carbon number 4. But it starts at carbon number 3. So we label both of those with the number 3. So 3-methyl and 3-hexene. So we can't remove the hex from the "ene" because, again, that's the root name. So putting it together, so again, we've gone through the 5 steps. Now we just have to get everything together. So the rule is for substituents, you arrange them usually alphabetically if there's multiple types of substituents. All right, but for the examples we'll have in class, we'll just have one each. And usually we leave the root name for last. So if we have 3-methyl and 3-hexene, again, we start with the substituent and leave the root name for last. We just shove them together with a dash in the middle. We have 3-methyl, 3-hexene. So this informs us where the methyl branch is and where the double bond is. All right, so even if you're given just this name, you should be able to write this structure. No matter where you are in the world, you should be able to come up with this kind of chemical structure from this name, right? So these are a few more examples. So 1,4-hexadiene. So hexadiene is the root name. So hex means there's 6 carbons in the chain. Diene because there's 2 double bonds. So the 2 double bonds are found at positions 1 and 4. So at position 1, at position 1 over here on the other side, we have the double bond. And for position 4, 1, 2, 3, 4, that's the next double bond. So again, the name shows the structure of your hydrocarbon. Even though it seems complicated, it actually simplifies things because the name itself actually helps us identify the chemical structure. Now it's time to talk about aromatic hydrocarbons. They have strong and pleasant odors, so that's why they're called aromatic. So if you've ever smelled a pencil pen or a marker, that's because it has a lot of aromatic hydrocarbons, and it's not good for your health. Don't huff them. Your aromatic hydrocarbons have benzene rings. What does that mean? This one on the bottom left is your benzene, the structure of benzene. So these benzene rings have what we call resonance. So resonance is when alternating single and double bonds in your hydrocarbon let the electrons jump between the bonds. What that means is, for example, in this diagram here, you can have the double bonds in this orientation, like on the left, or they can jump around and have this orientation. So since they randomly jump around at any given point in time, they resonate with each other so that it's like 1.5 bonds instead of one bond, single bonds and double bonds. Like everything resonates into like 1.5 bonds. So we just freaking draw that with a circle. Chemists, right? Just simplify things. Come on. So that resonance actually makes aromatic compounds more stable because the electrons, since they're jumping around different atoms all over the circular or the ring structure of the aromatic compound, it tends to not want to break apart. All right, so your aromatic hydrocarbons tend to be very stable. But is it really just carbon and hydrogen in your hydrocarbons? Are there no organic compounds with other elements? The answer is, of course, there's other elements involved. In fact, they're called functional groups in organic chemistry. This is extremely complicated, much more complicated than anything we've ever talked about so far. I've actually had to censor some in order to keep your sanity. So we're just gonna talk about these. So these are like less than half of the functional groups in total. But these are the most common functional groups in organic chemistry. So we also have our alkenes and alkynes here, so we'll skip those. Arene is basically let's zoom in here. An arene is just a benzene ring attached to your organic compound. A haloalkane is just the addition of a halogen. Alcohols just have OH added to the organic compound. Aldehydes, ketones, and carboxylic acids look very similar. They have a double bond to the O, but for aldehydes, the C that's double bonded to the O is connected to just a hydrogen on the other end. Ketones are connected to another alkyl group, which, by the way, R stands for an alkyl group. So let's zoom out. So an alkyl group is basically a branch of hydrocarbons. So just remember that that's just an arbitrary R. R is just an arbitrary replacement for a hydrocarbon branch. Okay. So going back, your ketones, your C and double bonded O are just between two alkyl groups. Your carboxylic acid has your double bonded O to your C that's bonded to an OH. So these look very similar, but they're very different. Like carboxylic acid, one example of a carboxylic acid is acetic acid. That's the acid in your vinegar, so you can put it in food. On the other hand, if you take the same alkyl group and you give it a ketone, so instead of acetic acid, you have acetone. Dude, that's the solvent that you use to take off super glue and take off nail polish. That definitely doesn't belong in food. So again, even though the functional group looks similar, even though it's just the addition of a double bond of O, very different functions. So the takeaway from this is that all these different functional groups, have a big effect on the properties of your organic compounds, depending on where they are, how many they are, and what kind of functional group is attached. So you should also be familiar with all these other examples, your ester, ether, amine, and amide. So thankfully, there's helpful diagrams such as these that you can go back to for review. Your carbon skeleton and all the functional groups together result in millions of possible organic compounds. That's why life and the products of life are so diverse. In fact, artificial stuff that we make like shampoo, soap, these are all also involving organic compounds. So, our different brands of soap and shampoo are thanks to organic compounds. So being simple and flexible is much more valuable than being big, right? So You don't have to dream big, for example, for yourself. It's actually better if you have very simple, very open-ended dreams. Like instead of saying, I want to be a doctor when I grow up, it's easier to say, I'm interested in anatomy. So you can be a doctor, you can be a scientist, you can be different types of things. It keeps your opportunities open, just like organic compounds having lots of potential. So I hope you guys keep your potential open, maximize your potential, and that's pretty much it for this topic. I'll see you guys next time.
Party's over.